I'm Paul Abruzzo. I lead forward deployed engineering for NVIDIA's AI Accelerator. AI Accelerator works with customers, some of who are probably in the crowd right now. But we're building out the infrastructure and solutions that actually show up on your cloud bill. So sorry about that. Uh, you're gonna hear a lot about tokenomics over the next couple of days. I figured I'd start you all out with something a little different. We're gonna talk about token production, right? So from training to fine tuning to inference, and hopefully, well, you'll take home a couple of notes that you can bring to your engineering teams on Monday. So just a couple of facts to set the stage here. In 2026 State of FinOps report said that 98% of FinOps teams are now dealing with AI spend. That number was 31% 2 years ago. The FinOps Foundation's mission has changed from the value of cloud to the value of technology. And AI cost optimization is the #1 skill most requested by FinOps practitioners. And the reason is pretty stark, right? GPU hours are not the same as CPU hours. We just figured out how to measure utilization for CPU, and now we have GPU hours to deal with. It's a lot of fun. But the problem here is that if you misspec a workload by 10%, say a training workload, it's not going to run slower. It's not going to run at all. So it fails, it out of memories, and you have to go ahead and requeue the job. You eat all of that expense. The cost of being wrong here is completely asymmetric, right? Because you have jobs running for days, weeks, if not months. Now we're going to talk about 3 different types of workloads. Just 3 archetypes here. We have pre-training workloads, right? These are the most expensive, the headline workloads, those 100K, 200K clusters that you hear about. Training randomized weights on trillions of tokens to produce foundation and state-of-the-art models. Most people in this room aren't going to be doing that. And honestly, you should not be. That leads us to fine-tuning. Fine-tuning is where I think enterprise can find a significant amount of value if you're looking to customize a model, right? You're essentially adapting a model to your data corpus or to your desired outcome. It's generally about 10 times cheaper than actually pre-training a model, but it depends on the methodology you use, and we'll get into that in just a bit here. And lastly is inference. We'll consider that the steady state workload, right? You train a model, serve that model, essentially infer trillions of tokens across millions of users, and implement your continuous improvement cycle. So to understand how to optimize these workloads, we actually have to take a look inside of the GPU. So we're going to take a look at how these workloads are distributed through GPU memory, right? If your engineers are talking about KV cache, key value cache, and optimizer states, this will become super relevant for you. So first, let's talk about those pre-training workloads, those absolutely enormous workloads. So how do you size those workloads appropriately? We're going to introduce a rule of thumb called the 16x rule. Now, there's a myth out there that trained model sizes, the weights as you might load them into an inference engine, would be the amount of GPU memory you'd need to actually train a workload. That is wrong. It's wrong by an extraordinary amount, orders of magnitude, exponentially so. Generally, the way we look at this is we need 16 bytes of GPU memory for every parameter in a model. And that's given the situation with mixed precision and a standard atom optimizer. Let's break that down, though, right? So you have the weights are actually only 2 bytes. Now, on top of that, you have the gradients, right? So 2 bytes for those. Those are the signals that kind of tell the model how to improve. Then we have the optimizer states, and those literally take up the other 12 bytes. The way that's broken down, Atom keeps essentially a high precision copy of the weights, and then plus 2 running statistics for every parameter, and those add up to your 16 bytes. Now, plus activations, which scale with batch size and sequence length, which can eventually actually exceed the trainable state required for the model, especially with long context workloads. The reality is stark, though. For a 7 billion parameter model, just to host the trainable state, right? So just the bare weights themselves, you're talking about 60 gigs. An H100 GPU has 80 gigs of GPU memory, so that only gives you a maybe 20 gig overhead for the trillions of tokens you're looking to train on top of that. Now, if you want to get even larger, you bring in multi-GPU sharding, the cluster network overheads, and the compute overheads that come with that. Just increase cost. Now, instead of pre-training, what we can do is fine-tune a model. You can think of fine-tuning like downloading a DLC pack for a model, right? You can give it a new mission, give it a new purpose. A full fine-tune requires the same 16 bytes per parameter as pre-training. But again, this is rarely needed thanks to some new advancements in how we train models. We have things called low-rank adaptation or low-rank adapters. LoRa's freeze 99% of the model weights. And it actually results in about a 70% drop in the amount of memory that's required to actually fine-tune that model. Now, even further, we can do a quantized low-rank adapter, which we actually take those frozen weights and then we quantize them to 4 bits, which affords us another 75% decrease in the amount of memory required. Now, the QLoRA paper actually cites a 65 billion parameter model that was trained on a single L40S GPU, a 48 gig GPU from the last generation. That would normally have taken tens, dozens, hundreds of those same GPUs to accomplish the same effect. Now, I know a lot of you are thinking, what about quality loss? And quality loss is absolutely a concern. You should always measure against your desired outcome. But what we find is that 95 to 99% accuracy on the trained data corpus can be maintained when training with LoRa's. So the FinOps question here, when someone comes to you asking for 8 or 10 GPU nodes, is not, what are you doing? It's one question: have you considered low-rank adaptation? Have you considered LoRa's or QLoRa's? Come on. Now, inference, right? This is the steady-state transition. Looks simple. It isn't. We load the weights once, and those are stored in GPU memory. But the variable cost becomes the key value cache, the KV cache, the model context. KV cache scales with batch size and sequence length, the number of model layers and attention heads. So, for example, a 7 billion parameter model with 32 layers and 32 heads at a 2,000 token context. And mind you, 2,000 tokens is absolutely nothing. It's probably the input sequence for a tenth of the prompt that you give your agents today. But that still requires, at full precision, 1 gig of GPU memory per concurrent user session. So that you can see how context and KV cache can very quickly outgrow the actual model requirements in that GPU. So what are the levers we have to tune that? So one is, of course, model weight quantization. So we can bring down weights from, say, bfloat 16 to FP8. That affords us a 2x memory overhead over BF16. But then we also quantize the KV cache, right? So KV cache quantization can take us, essentially we take that cache value, the exact same thing, we can reduce it down to FP8. And that will give us, again, more overhead to have 2 times the concurrency in the same GPU capacity. So really, the question becomes, how can we quantize these models to still have an acceptable quality level, to still meet our benchmark, but afford us more GPU memory and additional concurrency? Now, this technology is supported today in pretty much every major open source inference framework out there. So whether it's NVIDIA's TRT LLM, or SGLang, or VLLM, or even Llama CPP, these technologies are supported in all. All right, so I'm going to try to close this up as quick as I can. I'm going to give you 4 levers that you can effectively pull this Monday to talk to your engineering teams. The most expensive sentence in all of AI spend is, we always use H100s. The really important thing here, because you only get really one shot at this, right? Right now, all of your GPU capacity is committed spend constructs, 1, 3, 5-year commitments. So you have to suss this out prior to those commitments. Right size the skew. Understand what your desired outcomes are for that capacity and work backwards from that. You have to match the workload to the target silicon. This is the largest lever you have to actually reduce costs. For example, pre-training, fine-tuning workloads. Those are the big GPUs, the H100s, H200s, B200s, B300s. That makes sense. They can be up to 3 times faster for training, 10 to 15 times faster for inference workloads. Again, if you're taking advantage of their key technologies, which is usually reduced precision acceleration. But let's say you're just doing inference for a 7 to 13 billion parameter dense model, or a recommendation engine, or a small multimodal model. It might actually make more sense on a per request basis to hone that on an L40S or an RTX Pro 6000, which you can get in your hyperscalers today. The bottom line is kind of unused HBM and compute capacity is wasted money. This is an opportunity for us to right size. Again, quantization and precision. This is a really big deal for us. These are the silent savings. We're not in the CPU era anymore. We're not looking at full precision for everything. Not everything is FP32. We generally standardize on bfloat 16, right? Half precision, which allows us 2 times the memory overhead for these workloads over what we might experience if we were running FP32. FP8, which again halves that precision, which is native on Hopper and Blackwell, gives us another 2 times the memory overhead, right? So both for training and inference. Now for those inference workloads, again, we have those options to quantize the model weights, allowing us to fit more model in a single GPU or in a GPU cluster. Again, FP4, FP8 inference, this gives us another 2 to 4 times GPU memory overhead, so long as you're managing your quality budget. So the question isn't like which precision should I use? It's, are we leveraging the lowest precision possible for our workload? Are we leaving lower precision on the table? If you're paying for an H100, a B200, a B300, and you're not taking advantage of the premium feature, you're at a loss. Again, and don't come at me about this. GPU utilization is a real big deal. If y'all want to talk about how to calculate and how to properly report on GPU utilization, we can have a 2-hour discussion during this, this party.
Hey, Paul, we have 20 seconds.
20 seconds. Okay. So really, folks, what I want to go ahead and leave you with is just 6 questions you can ask your FinOps or your engineering team. What's the model archetype, right? So is it a pre-training workload, a fine-tuning workload, or an inference workload? Number 2, what is the parameter count? What is the parameter count and the GPU memory used based on our implied assumption, our rule of thumb? Number 3, consider cheaper techniques, right? LoRA over full fine-tuning, QLoRA over LoRA, and by the way, prompting over QLoRA. Sometimes you can just prompt your result. Number 4, at what precision? Are we leaving lower precision on the table? Generally, we're leaving money on the table. Number 5, is the SKU right-sized? Are we using the right silicon for the workload? Number 6, how are we measuring utilization, and how do we report it back to our FinOps organization? If you ask these questions prior to committing to 1, 3, and 5-year committed spend constructs, you will effectively catch most of the over-provisioning before you actually commit. Start a real conversation with your engineering teams and avoid the budget tug-of-war. I appreciate everyone's time today.